We are back to pick up another example of graphing a rational function with all of the details. So it's like following the 7-step or 6-step or whatever many step method. The first step that we had done was we were going to factor and list the domain. Okay, so g of x would equal, there's a GCF of x, so x times x plus 2, and the denominator stays x minus 1. So there's this factoring. Then what we need to do is list the domain. For the domain, we set the denominator equal to 0 to get restrictions. Okay, just as a reminder, I'm going off of this sheet of notes that we did in the last video. So if you don't have that, I'm kind of doing a few little refreshers as we go. So I say x minus 1 equals 0. So x equals 1. So this domain, this is our domain restriction. So the domain would be all the numbers of x such that x does not equal 1. Or in interval notation, which is my preferred way, we go from negative infinity to 1. That's a positive one. And then from 1 to infinity, because we have to exclude the value of 1. So that's our first item. Our second item is wholes. And remember that wholes come from canceling a common factor. So if we look at our factored form, there's nothing we can cancel. So that means there are no wholes. The third step in our process was x-intercepts, and y-intercepts. So x-intercepts we are going to find by setting the numerator equal to 0. Y-intercepts we're going to find by subbing in 0. I guess this is g of 0. So x-intercepts, we set the numerator, x times x plus 2 equals 0. So x equals 0, x plus 2 equals 0. So we've got 0, 0, and negative 2, 0. Y-intercepts, finding g of 0 would be 0 times 0 plus 2 over 0 minus 1, which is, oh my goodness, 0 over negative 1. So still 0. So 0, 0 for the x-intercept and y-intercept. Next up was the vertical asymptote and limits on both sides. So to find the vertical asymptote, we set the denominator equal to 0. So we've got x minus 1 equals 0, which gives me x equals 1 for my vertical asymptote. And then I'm going to kind of draw that in there, and I need to figure out the limit as x approaches 1 from the left of my function, x times x plus 2 over x minus 1, and the limit as x approaches 1 from the right of my function. And we have done that by subbing in a value a little bit to the left of 1, so like 0.99. And a value a little to the right of 1, it's like 1.01. And then figuring out if that function is headed towards positive infinity or negative infinity. So we really only care about the signs in this case. So the sign for the x, 0.99, is positive. The sign for x plus 2 is also positive. But the sign for x minus 1, 0.99 minus 1, is going to be negative. So on the left-hand side of 1, we are going to end up with a negative value. So that's headed to negative infinity. So on the left side of my asymptote, the function is going to be down. On the right side, this x value is going to be positive because it's 1.01. X plus 2 will be positive, and x minus 1, 1.01 minus 1 is also positive. So on the right side, my graph is headed towards positive infinity. The fifth step, this is the horizontal and oblique asymptotes. And to determine that, we need to compare the degrees. The degree of the numerator we list as n, the degree of the denominator we list as m. So then our guidelines are, if the numerator is less than the denominator, we have a horizontal asymptote at y equals 0. If the degree of the numerator is equal to the degree of the denominator, we have a horizontal asymptote at y equals, we're going to look at the leading coefficient of the numerator divided by the leading coefficient of the denominator. If the degree of the numerator is 1 higher than the degree of the denominator, then we need to do long division, and we're going to have an oblique asymptote at y equals the quotient that we get. And if the degree is 2 or more higher, then we will just say there is no oblique asymptote or horizontal asymptote. So in our problem, the degree of the numerator was 2, the degree of the denominator was 1. So the degree of the numerator is 2, denominator is 1. So it's not going to fall into this category because n is bigger. It's not falling here. N is going to be 1 plus m. So we need to do this long division. Okay, good stuff. So we're going to start by putting the numerator inside the division symbol and the denominator outside. And I will run you through a long division problem. So we're going to start out by taking the first term in the dividend over the first term in the divisor. So I'm going to do x squared over x, which gives me x. So I'm going to take this x and I put it up here in my quotient. Then I'm going to multiply that x times the divisor of x minus 1, and whatever I get, I'm putting in this row. So x times x is x squared, x times negative 1 is minus x. Then the next thing I'm going to do is I am going to change both of these signs. So I'm going to change this sign to negative, this sign to add, and then I'm going to combine like terms moving down. So that will give me x squared minus x squared cancels. 2x plus x is 3x. Then I'm going to repeat what I had just done. I'm going to take the first term on this row divided by the first term in the divisor. So 3x over x gives me 3. This becomes a part of my quotient, and it is positive, so it will be plus 3. Then I multiply times the divisor, x minus 1, and I put that in this row. 3 times x is 3x. 3 times negative 1 is negative 3. I change both of these signs. The 3x and the negative 3x cancel, and I end up with 3. Now, once I get this constant term here, I'm done doing division, and this is going to be the equation for my horizontal or oblique, well, it's oblique asymptote. So the quotient gives me my oblique asymptote. It is at y equals x plus 3. The next step on our list is the sign chart. On the sign chart, we're going to put our vertical asymptote, any hole, the x values for holes, the x values for x-intercepts. And then we're going to check to see if the function is positive or negative. So we make our little sign chart. Vertical asymptote, we had x equals 1. We didn't have any holes, and our x-intercepts were at x equals 0 and x equals -2. So we're going to put those values on here. -2, 0, 1. I could have spaced that better. That's fine. Then we pick a number in each section. So maybe x equals -5. So if I put -5 into my function, I kind of prefer the factored form, but it doesn't matter. You can use either. -5 times -5 plus 2 divided by -5 minus 1. So that is -5 times -3 over -6. That is 15 divided by -6. So -5 comma, I'm going to get a calculator because I'm going to make this into an ordered pair that I can add to my graph. That is -2.5. So that's going to also tell me that my graph will be below the x-axis from -infinity up to -2. Pick a number between -2 and 0. How about -1? So y will be -1 times -1 plus 2 divided by -1 minus 1. So that is, what do we got? -1 times 1 over -2. So -1 for the x value and 0.5 for the y value. So the graph will be above. And then between 0 and 1, how about 0.5? So y will be 0.5 times 0.5 plus 2 over 0.5 minus 1. So that is 0.5 times 2.5 divided by -0.5. So that's going to give me the ordered pair, 0.5, -2.5. And in this last section, so also that means that it's below because the y value was negative. So then we can pick maybe x equals 2, maybe 3, pick what you want. So we'll have 2 times 2 plus 2 divided by 2 minus 1. So that is 2 times 4 divided by 1. So 2, 8. So we are above. So this guy is going below, above, below, above. Okay. Then the next thing we're going to do is put all of our information on the graph, and we're also going to check to see if our function crosses the oblique asymptote at any point. So things that are going on the graph will be the holes, which there aren't any, x-intercepts and y-intercepts, the vertical asymptote at x equals 1, along with what side, which direction our function is headed, the oblique asymptote as a dashed line, and then I'm going to pay attention to the above, below, and I'm going to add these extra ordered pairs on there. Okay. I kind of cheated and paused the video and drew my axis. So you can pause the video and catch up, and then join me back in. So deciding whether the graph will cross the horizontal or oblique asymptote, what we do is you set your function equal to the asymptote itself and then solve. So our function was g of x actually, and it was x squared plus 2x over x minus 1. And our oblique asymptote was y equals x plus 3. So we're going to solve that and see if we come up with a numerical value or not. So multiply both sides by x minus 1. Gives us x squared plus 2x on the left side. And we're going to have to FOIL the right side. So that'll be x squared plus 3x minus 1x. So plus 2x and then minus 3 on the other. Then if we subtract x squared from both sides, we get 2x equals 2x minus 3. Subtract 2x. And we get 0 equals negative 3. Since that's not an x value, that tells us that no, the graph will not cross the oblique asymptote. So we are ready to get started with our graphing. Since there were no holes, we will start by putting the x-intercept and y-intercept on there. And those were at 0, 0, and negative 2, 0. Then let's get the vertical asymptote next, which was at x equals 1. So at x equals 1, I need a dashed line on the left side. The graph is going to be headed towards negative infinity on the left side of that asymptote and headed towards positive infinity on the right side. Next up is our horizontal and oblique asymptote. This one was oblique. It was y equals x plus 3, which means we have an x-intercept at a y-intercept at 0, 3, and a slope of 1. So, and keep in mind that this is also a dashed line. Okay, so there's my oblique asymptote. And also keep in mind that your graph does not cross this horizontal and oblique asymptote. So as we put our ordered pairs in there, we've got to kind of pay attention to knowing that it's not going to cross. Okay, next ordered pairs on there. Well, we've got our sign chart with above and below, and then we've got a few extra ordered pairs. So in between negative infinity and negative 2, our graph is going to be below the x-axis all the way up to negative 2. Then in between negative 2 and 0, it's above. And then between 0 and 1, it's below. And then 1 to infinity, it's above again. I guess I should have put my below down here. That would have made more sense. All the way up to here. Okay. As I'm drawing my graph, keep in mind I have to connect to this arrow. I have to go through this point, and then I'm above. I have to go through this point, and then I'm below, and then I'm going to run along this asymptote. So, and not cross it. So, let me connect my dots here. So I'm going to go along this arrow, up through this point, above, and then down below, like that. Oh, you know what I forgot? My extra points, y'all. Negative 5, negative 2.5. What am I thinking? I'm not thinking. That's the problem. So negative 5, 1, 2, 3, 4, 5, negative 2.5. 1, 2, 3, 4, 5, 1, 2.5 right there. Well, I almost hit that point. And then negative 1.5. Ooh, I did pretty good there. 0.5, negative 2.5. 2, got that one. And then 2, 8 is my other one. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now I only have that one ordered pair in this section, but I also know that my graph has to go towards positive infinity here, and it doesn't cross this orange line. So I can get a sketch knowing that it has to go through that ordered pair, and then it has to turn and go along this asymptote. If you would like to, you can add some extra ordered pairs by doing like an XY chart, kind of like we did with our sign chart, just picking different x values to get more ordered pairs. But for what we're doing, this is accurate enough. I just need to see all of those ordered pairs and all of those features of the graph that we went through in our list.